Today we're going to talk about the other type of bonding, known as covalent bonding or molecular bonding. This involves when we have more than one atom that's actually sharing electrons. And this only happens between nonmetals. So if you happen to see a metal in there, you automatically know that it's an ionic bond. This is where we actually have electrons being counted more than once to be able to make up that valence shell. With these two oxygens here, we happen to have one oxygen, two oxygens, three oxygens, 4, 5. This one here that's shared gets counted towards that first oxygen on the left. So that's 6, 7, and 8. When we happen to be looking at the second molecule, we see the same kind of thing. We have 1, 2, 3, 4, 5, 6, 7, and 8. So those two electrons that are in orange there, those are actually shared in between the two sets of oxygen. And since they can share it, they both kind of claim it as filling out the valence electrons. This is how we're able to have compounds actually be able to form and fill those valence shells by sharing electrons. There are some that are only found together. We call these diatomic molecules. This is because these ones will never be found as like a single oxygen or a single hydrogen. They're always found in pairs. So one way that we can help remember what those things are that are always found in pairs is by using the term Hoffenbrinkel. So each one of those letters actually stands for the element that's found as a pair. So H for hydrogen, O for oxygen, F for fluorine, I for iodine, N for nitrogen, Br for bromine, and Cl for chlorine. Hoffenbrinkel. You'll notice that these are all nonmetals, and these are also mostly our gases in the periodic table. When it comes to trying to name what these are going to look like, we have a little bit of a different way of doing it than we did with the ionic compounds. So the one that is on the left of the periodic table is going to be the first one. The one that's on the right is going to be the second element. That's how we write those things down. It's just kind of following along the places that it has in the periodic table. We also have prefixes. That pre is telling us that there's something that we put before the element in order to help us understand how many there are going to be in the element. And that fix is just because we're fixing it onto that name. And then just like we did with ionic compounds, we're going to change that second element and drop the ending in order to add an IDE onto the end of it. So here are some of the prefixes. Some of them might look familiar. Mono is talking about one. We only usually use this when we're talking about oxygen, and a lot of times we'll just leave it alone and just write down the element name if there's only one of them present. Di is 2. Tri, like tricycle, is 3. Tetra, penta, like pentagon. Hexagon, hexa. Hepta, octa, nona, and deca. So see that these have a lot of overlap when it comes to how you would talk about the number of sides that something would have in math. Take a second and see if you could figure out what the names of these compounds are. Just pause the video here. For this one, since we have only one sulfur, we would just leave that name there, sulfur. And since we have 6 fluorines, we would put that hexa prefix right before we actually write down fluorine. Since that's the second element, we also drop the ending and add an IDE to show that this is actually a compound. What about for this one? Pause the video now and try and figure it out. For this one, we actually have 2 nitrogens, so we're going to need one of those prefixes. And we've got 5 oxygens. So we're going to use that di prefix in front of the nitrogen, and that penta, we drop the A because there's an O, in front of the oxygen. Now oxygen, we cut it off right after the OX when we add that "ide" there in order to get oxide. If we're going to be drawing the Lewis dot diagrams for this, we draw it in a similar way that we did with the ionic bonding. We'd start off with an element. If you've got one element that's just by itself along with multiple of another one, that lone element's probably going to be in the middle. And then we happen to draw the different electrons around. I use 2 different colors here just to show which ones are coming from oxygen, which ones are coming from fluorine. But you can also use anything, little X's, little hollow dots, any way that you want to show the difference between which electrons are from oxygen and which electrons are from fluorine, or whatever elements that you happen to be drawing these for. When we happen to have a pair of electrons being shared, like we do here, one way of actually showing that pair of electrons is to draw a straight line here to show that they're bonded together. So that sharing is actually what creates that bond here. With ionic, it was that magnetism, so having one positive, one negative, and having them attract together because they were oppositely charged. For here, we get bonds because things are actually physically connected together through that sharing of electrons. And so rather than drawing those two electrons between oxygen and fluorine, we can actually represent that by drawing a straight line for the bond. Try drawing these covalent bonds to see how your loose dot diagrams might compare to others.